Hello students, welcome to YourPedia Education. My name is Arun Pathania and today I have brought you this video in which I am going to discuss in detail the solution of a question given in the NPTEL assignments for the branch of civil engineering. So students, as you must know, these questions that are given in the NPTEL assignments are very important. There is a direct correlation between the questions that are given in the assignments and the question that come in the GATE exam. So what we have done, what YourPedia Education has done, is that they have taken these questions and compiled them systematically into books like these, okay, for various branches. This is for civil engineering branch. So what I have done is I have taken a question from the RCC subject, question number 86, and I have prepared the detailed solution of that question for you. And in this video I am going to discuss the numerical part of that, and I will also explain the whole concept that is behind that question. Okay, so let us just start. So the question is, we have been given a rectangular beam of these dimensions, which is pre-stressed by a means of 4 numbers of high tensile bars, which are located 200 millimeter from the soffit of the beam. Now what is the soffit of the beam? It is actually the base of the beam, okay, on which the beam rests. Now effective pre-stress has been given to us. We have been asked what is the maximum bending moment that can be applied over this beam so that there is no tension without causing any tension at the soffit of the beam. Now students, you know this thing, whenever we have a beam and there is a superimposed loading over this beam, then what happens is this beam bends. Because of this bending stresses will develop. Okay, so if this is our cross section and this is, I'm marking the neutral axis, so what happens is this portion above the neutral axis will be under compression and this portion of the cross section below the neutral axis will be under tension, which I can represent like this. Okay, it will be under compression and it will be under tension. So this is the variation of the bending stresses in the cross section. So if you can see, the maximum tension will come at the extreme fiber below the neutral axis at the soffit of the beam. But what is happening here? Here we are pre-stressing our concrete so that no tension comes at the beam, at the soffit of the beam. Okay, but there is a limit. You know, there is a limit to the maximum bending moment that can be applied over the over that beam, because depending upon whatever magnitude of the pre-stress we are giving, so there is a limit over the maximum bending moment that can be applied so that there is no tension. I'll explain that how these stresses gets arranged and how this tension gets completely nullified and neutralized by the application of pre-stress, but in the coming slides. Okay, so let me first tell you what is pre-stressing, what is this concept. Okay, so yes, pre-stressing is the process of introducing stresses, internal stresses of desired nature and magnitude. Now this line is very important. I'll explain why. So we have to introduce stresses of desired nature and magnitude, desired nature, okay, according to what we want. Desired nature and magnitude we are introducing in a material so as to counteract the stresses developed due to the superimposed loads. Now this is very important. So what we are doing, because of the superimposed loads, some kind of stresses, some stresses of certain nature, either tension or compression, are going to come inside a material. Okay, so what we are doing is that we are introducing certain stresses beforehand, so that what can happen is, and the nature of stresses that we are introducing is opposite to the nature of stresses that are going to develop due to the superimposed load. Okay, so what will happen is that the stresses that we introduces will neutralize the stresses that are going to come because of the superimposed load, and because of this the efficiency of the material will increase. Now our structure can take much larger load than it could have taken earlier. So this is the concept of pre-stressing. Now this concept of pre-stressing is not a very new concept. It's not something that we have developed recently. This concept was known to mankind and was used by mankind from a very long time. Okay, so if you might have seen in movies or somewhere, you might have seen wooden barrels. So in earlier times when plastic was not known to man, and metal was very costly, then it was difficult to make these containers to hold liquids or water or suppose grains. So what we do in that time, we have a lot of timber available to us. So what we do is we take these wooden planks and then we bolt them together to form this shape of this container, of a cylinder. As you can see in this picture, how these wooden staves and planks are bolted together, are joined together to make this cylindrical shape so that we can store water or liquid in it. Okay, so this is a wooden barrel. So what happens is this now acts as a thin cylinder, and if you have studied strength of materials, you know that whenever a thin cylinder is subjected to internal pressure due to any liquid or a fluid, then hoop tension and longitudinal tension develops in that particular material. So because of this hoop tension and longitudinal tension, the cylinder will try to split open. Because of this, the liquid will spill, and the whole purpose for which this container was designed will be defeated. We don't want that. So what people did back then, they took basically steel bands, metal bands, they took circular metal bands they took, and they heated those metal bands, and because of heat, the metal expands, their size increases, and now they can easily fit on the outside of the container. As you can see here, these metal bands are basically placed. Now with the time, when the metal cools down, it will try to regain its original size. It will try to contract. So what will happen when it will try to contract? Now this wooden planks will not allow it to contract. It will say that you remain in your position, because buddy, I'm here, I will not allow you to move. So what happens is these wooden planks are applying tension over these metal bands, and these metal bands are trying to contract, so these are applying compression over these wooden planks. So this wooden planks was originally under tension because of the water that is being present in it. So this was originally under tension, and because of these steel bands, now compression is coming over them. So this compression will neutralize the tension caused by the water that is present inside them, and because of this, now this barrel or this cylinder can now store more water and can now be stable. So this is one of the concept where pre-stressing was used, where we have introduced stresses of desired nature, of a type which is opposite to the kind of nature that are going to develop or come because of the applied loading. So this was one of the examples that you can see. Now this is the pre-stressing that we have used in case of wood and metal, but the pre-stressing in case of concrete, because in a question the concrete beam is basically pre-stressed. So the concept of pre-stressing concrete is comparatively a newer concept, and it was introduced by Fressinet some time ago, and then it became very popular. Now my question is why have we developed RCC? What is the use of developing the reinforced concrete? You all know that concrete is a material which is very strong in compression, but it is not that strong in tension. So what happens is, as I explained earlier, so when these superimposed load acts over suppose a beam, when it will act, then what will happen that some part or some portion of the cross section will develop compression, and some portion will develop the tension. Now the tensile strength of concrete is not that large, so what will happen that it will fail at, now this, if I look at the strength, this is the strength of the concrete. So in compression, suppose the strength is this much, suppose 30 MPa or 20 MPa depending upon the grain of concrete, but if you look at the tensile strength, this is very small, only about 10 to 15% of the compressive strength. So what will happen, it will fail at a much lower stress level as compared to compression. Okay, this lower part will fail at much lower stress, so tensile cracks will develop, and these cracks will then propagate and reach up to the neutral axis, and the whole beam will be cracked, and then it can't be used, it won't be able to take the loads. Okay, in order to solve this problem, we introduce a steel reinforcement. You all know that, that's why we have developed the RCC, that's why we study this subject. Now what is the reason of, now we already have increased the tensile strength of the concrete by introducing this steel, okay, and if we are not satisfied by the steel that is provided in the tensile zone, we sometimes provide steel in the compression zone also. We have doubly reinforced beams. Now the question arises, what is the need of going with the pre-stressed concrete? Okay, when we have reinforced concrete, what is the need of going with pre-stressed? Now why we have developed this pre-stressed concrete is, listen me very carefully. So what happens is, as I have already told you, that suppose this is a concrete beam. So what happens is, below the neutral axis, tension is going to develop if it is a simply supported beam. So here these are steel reinforcement is provided. Now the tensile stress will be maximum. Tensile stress will be maximum at the extreme fiber, at the soffit of the beam. The tensile stress will be maximum. Now suppose the tensile stress strength is suppose 3.5 MPa. If I say it's suppose let's say 3.5 MPa it is. For maybe M25 concrete. So what will happen when the tensile stresses at this level will exceed this much value, the concrete will fail. The concrete will fail and the crack will start to develop. Tensile crack will start to develop. Small cracks will start to develop and they will go upwards. Okay, as we in plain cement concrete this happened. Now what is different in reinforced concrete? The presence of these steel bars. Because of these steel bars, now what will happen when these cracks will reach at this location, these steel bars will take the tensile stress, and now the concrete doesn't have to carry the tensile stress. Steel bars are carrying the tensile stress. So these cracks will not propagate further. These cracks will stop at this location only. So what was what was required? That we have to provide these steel bars at the extreme fiber only. If we would have provided the steel bars at the extreme fibers, then no tensile crack would have developed in the first place. You know, for some small region, these tensile cracks have formed, and now it will be problematic from the durability point of view, and it can cause the corrosion of the steel reinforcement also. I mean, there is problem because of these tensile cracks that we will discuss later. So these tensile cracks would have been, I mean, they would have been completely eliminated if we would have provided these steel rebars at the extreme fiber, but we can't do that because we need to provide some cover. Otherwise, you know, fire for the purpose of fire resistance, for the purpose of saving the reinforcement from the corrosion, we can't provide it at the extreme fiber. We have to provide some cover, and in that region of the cover, these tensile cracks will develop. And now tensile cracks will be difficult it will be problematic for the concrete from the durability point of view. Moreover, this is what we are talking in case of static loading. You know, when the loading is static, as we seen in the beams in our homes or something. But when the loading is not static, say it's dynamic, suppose in industrial beams in industrial buildings where there is a large vibration, or say in case of bridge girders, you know, there is dynamic loading over there. There is a lot of vibrations and all. So what happens is these cracks will propagate no matter what. Okay, you might have provided the right amount of steel over here, but these cracks will develop, will still propagate because of some changes in the microstructure, because of the shocks that and the vibration that the beam is basically receiving. So in that case, we need to further strengthen our RCC beam. So how did we do that? We provided the pre-stressed concrete. We pre-stressed the beam. So in this way, this material was developed to further improve the properties of the reinforced concrete. As you can see from the picture, this is plain concrete. Plain concrete to simply will crack when superimposed load will act on it. When it will bend, it will simply crack. So in order to to save that from cracking, save that from failing, we provided reinforced concrete. But reinforced concrete will still crack up to this location, and sometime up to neutral axis if the loading is dynamic in nature. So in order to prevent that, in order to further strengthen the reinforced concrete, we provide pre-stressed concrete. Now the pre-stressed concrete will not fail and will also not crack. So the failing is also important and the cracking is also important, because cracking is also one serviceability criteria in RCC, if you can remember. Okay, so it will also not fail and it will also not crack. So that's why pre-stressed concrete is better than both plain concrete and reinforced concrete. Okay, so now I have to explain you the concept how it is able to save this from cracking. So what happens is, as we know, let me change this slide. So what happens is the beam is under tension. So what will happen? Is under bending. So it will develop compression on the upper portion and tension on the lower portion. So say this is compression, some value of compression. Now what compressive stress will it develop? Okay, what is the maximum value of compressive stress that a beam will develop? We have to use the concept of M upon I. This is the flexure equation, M upon I, sigma upon Y, E upon R. From here we can see that the bending stress at any location which is at a distance y from the neutral axis is equal to M upon I into Y. Bending stress at any location you can find from this formula, where M is basically the bending moment at that location. So if I am going to find at center the bending moment will be maximum. So at center, if I am going to find what kind of stresses or what amount of stresses will come or at this location, at the soffit of the beam, at the center of the beam, at the midpoint of the beam, but at the bottom fiber, at the midpoint of the beam, at the bottom fiber. So for that, what I have to use, I have to find the in that case I put the y is equal to what, the depth ka half. I put y is equal to d by 2. In that case I get the theta max is equal to m upon z, where z is equal to the section modulus. Okay, Z is equal to the section modulus. This you must have read in strength of material. So from this particular expression we can find the value of the maximum stress that is going to come at the soffit of the beam. Okay, this gives us the magnitude. So this I know compression will also be equal to M upon Z and tension will also equal to M upon Z. So now what we are doing, we are pre-stressing the concrete. How pre-stressing is done? Either we are using the pre-tensioning or we are using the post-tensioning. So what is pre-tensioning, post-tensioning? I'll explain. So what happens is, suppose the steel bar is present. So steel bars is present and we provide tension in the steel. We are providing tension in the steel. Now you can ask, sir, you said that we are going to counteract the tensile forces. Why are you providing tension in steel? You must provide the compression. Now the question is, if you remember, I am saying we have to neutralize tension in concrete, not in steel, because steel can take both tension and compression, but concrete can't take tension. So what happens is, by tensioning the steel, what happens is we are trying to tension the steel. Now steel is in direct contact with concrete. When one material, one portion is under tension in a composite, the other portion or the other material will experience compressive stress. So the concrete will now come under compression, because concrete is in bond. There is a bond between the concrete and the steel. So when steel will be pulled out, the concrete will be under compression. So because of this compression, compressive stresses will come in concrete, and these compressive stresses now will neutralize this tensile stresses. So though two cases can happen. What first case is, suppose there is we have provided the this steel tendon at the neutral axis only, at zero intensity, at the center only, and now we are pulling it out. So we are pulling it out because we are introducing compression in the concrete. So let me write like this. Actually we are putting it out, but this is basically the compression will be induced in the concrete. So I have put the sign like this. Okay. So what will happen is, suppose this is the cross section is B by D. The cross section is B by D. Cross section of this beam will be B by D. So what will happen? It will introduce compressive stresses. So what compressive stress? Since it's an axial force, the compressive stresses will be same throughout the cross section, and it will look like this. This is the whole cross section. This is the D depth. This is the cross section. So the compressive strength variation will look like this, and the value of this will be P by D, P by BD. Okay, load upon area. This is the value. This is the compressive stress that will come. Now this compressive stress will be added to this bending stress, because both are normal stresses. These can be added. So when this will be added to this will look like this. So the final thing will look like this. Either this, or it can go up here depending upon what is this magnitude and what is this magnitude. It can either look like this, it can either look like this also. Okay, so that depends. So we also have to control the magnitude. In the beginning I said we have to introduce these stresses of desired magnitude and nature. So nature I explained how it is different. Magnitude is why magnitude is important and why it has to be controlled, so that this thing doesn't happen. Our compressive pre-stress, the stresses that develop due to the pre-stressing should be larger enough so that there is still no tension here. It can go like this, but it should not go like this. Concrete can take compression, but concrete can't take tension. So it should not go like this. It can go like this. This is one way of doing this. Okay, this will still have some strength, but it will not have that much effect. There is another way we can improve the efficiency, and what we can do is, rather than providing our tendon and pre-stressing it at the neutral axis, we can provide our tendon below the neutral axis. And then pre-stressing it by P force. Okay, what will happen now? It is at some eccentricity. Now what will happen? This will create a moment. This will create a moment on both the sides. Now both these moments are of hogging nature. So they will try to bend the our beam like this. Now what will happen? At this location tension will come, at this location soffit of the beam compression will come. So what will happen, in addition to this, this though will develop, because this can be translated over here. So if this is P force, and it is acting at some eccentricity, so what will happen, this can be translated to there, and the equivalent diagram can be P force at the neutral axis, moreover moment of P into E, P into eccentricity. So this is equivalent to this. Suppose this is the neutral axis. If this is the neutral axis, this is the neutral axis. So if we are doing this, this is equivalent to this. It will also have one axial load, and it will also have one hogging moment. So we are getting this compressive stress also, and we are getting this also. Because of this, up in top we'll have tension, and in bottom we'll have compression, and the magnitude of this will be PE upon Z, because it's mz only. And what is the value of m? M is basically moment is basically PE upon Z here. So now it is creating tension here and it's creating compression over here. Now instead of adding only this, we have to add this also. Now what will happen if I add this also? Now there will be less. Now if you see, compression, large stresses come over here. Now there is also a limit to how much compression a concrete can take. We don't want to exceed also, and we don't want कि हम लोग उसको बचाने गए in tension and it fails in compression. We don't want that also. So what we can do is कि now we have reduced this also. This also get reduced, and this gets like this becomes more or less uniform. Okay, it was here earlier, it got some and it got reduced by some amount, so it become like more or less. It will either become uniform, or it will become like this, or it will become like this, but more or less uniform. This is basically what we want. We want a more or less uniform compression in concrete. We don't want too much compression also. We don't want even a little bit of tension also. Okay? We want that only compression should come, but compression should also not be very, very high. Compression should be like under some limit only. So almost uniform stress distribution that you got all over the cross section. This is what pre-stressing does, and this is what this eccentric pre-stressing is helpful in. We can either go with concentric pre-stressing where we are applying the pre-stressing at the neutral axis only, and we can also go with eccentric pre-stressing also. Okay, that depends upon the what kind of loading it's coming. So this pre-stressed concrete has become very popular to be used in case of bridge girders, and in case of these whichever building, in case of these cable stayed bridges also, especially in bridges and industrial buildings, because these are subjected to dynamic loading, and in dynamic loading pre-stressed concrete behaves is very much, its efficiency is very good as compared to reinforced concrete, and it is also economical for higher spans as compared to reinforced concrete, because what will happen now, the stresses have reduced. We can see, so we don't need not to use as much, we don't need to have larger cross sections, okay, because stresses are less only, so we need not to design very large beam, we can design small beam also. So obviously there will be very large saving in terms of economy also. So I mean, if we compare both the RCC and PCC comes out to be economical for bridges and industrial buildings, but not for domestic buildings. So domestic buildings we use RCC only. Okay. Now there are two ways in which pre-stressing is done. We can either go with pre-tensioning. Pre-tensioning means concrete is placed after the steel is tensioned. So we have already tensioned the steel, then we place the concrete. After the concrete sets and hardens over time, then it develops compressive stresses, and that we have. This is called pre-tensioning. Pre-tensioning is generally used for precast members. Okay? It can't be done at site. The second method is post-tensioning. In post-tensioning, we had already cast the concrete and we have left these ducts or holes in the beams, suppose. Okay, and then we later on we take these steel tendons, and then we put tensile stress over them. We try to pull them out. Okay, so that is post-tensioning. The concrete has already been cast. Now this can be used for precast also. This can be used at the cast in situ members also. So these are both the methods that I have explained, and this is the concept that we have, which I have also explained. Now coming on to the question, because we have to solve the question first. So the coming on to question, let me first draw it. So what we have is, basically we have a beam जिसका जो dimension है that is basically 250 mm, and this is 600, and okay, 4 numbers of high tensile bars. We always use high tensile bars for this. Now let me tell you also the reason why don't we use mild steel for this, because there will be pre-stress loss. A lot of pre-stress that we have provided, the tensile stresses that we have, with which we have pulled this steel out, a large percentage of this would be lost. Okay, so we want कि still some will remain, so we use high tensile stresses, so that their tensile strength is about 1200 Newton per millimeter square or 1500 Newton millimeter square. So we pull them up to this or stress them up to this level, so that even if 200 or 300 Newton per millimeter is lost due to certain losses, then still we have a sufficient amount of pre-stress with us. But if I use mild steel, and the mild steel, the permissible value of stress is basically 140, 130, and out of this 140, 130, the all will be lost only. Okay, so I'll be left with no pre-stress only. That I don't want. So I use high tensile stress bar. These can be tensioned to a higher level, and then even after losses, they will have sufficient pre-stress left in them. Okay. Now these have been given 4 number of 10 mm dia, this high tensile steel bars. These are at a distance of what? These are at a distance of 200 millimeter. So the centroid ka distance from the soffit is basically 200 millimeter. So as we can see, the neutral axis will be at a distance of 300 from the top also and from the bottom also. So now can you find the eccentricity of these bars? Yes, I can find the eccentricity. Eccentricity will be the distance from the neutral axis, and now this distance will be 300 minus 200. So eccentricity will be equal to 300 minus 200, or 100 millimeter. So the eccentricity will be 100 millimeter. So now we have eccentricity also, we have this thing also. now we can find we can find the stress distribution. Okay, so what we have is let me find the now pre-stress has been given to be effective pre-stress. Pre-stress after the losses that we discussed now, effective pre-stress has been given to be 500 Newton per millimeter square. So if I ask you how much pre-stress force was there initially, कि कितने लोड से हमने उसको खींचा होगा initially, obviously we have to do what? Area into the stress. So the pre-stressing force will be area into stress. Now this area will not be the area of the concrete, because the whole concrete beam is not being pulled out. Only the steel tendons are being pulled out. Okay, so this stress will be 500, and the area in this case will be the area of the cross section area of the high tensile bars. Okay, so this will be pi by 4 into 10 ka square. This will come out to be 500 into 5 into 100. This come out to be 157,250 Newton. Okay, so this was the initial pre-stress force with which we was pulling it. Okay, now I'll move on to the next. So now let's do what we have to do is, now we have been given that there should be no tension at the soffit of the beam. So for the no tension at the soffit of the beam, we can write stresses at the soffit. Now what will be the stress at the soffit? This stress must be equal to 0. This stress must be equal to 0, so there should be no tension. Okay, so what will happen now, I have already explained earlier that because of superimposed loading, what stress will come at the soffit? Tensile stress will come at the soffit, so it will be taken as negative. I am taking tension negative, compression positive. And what will be the magnitude of this bending stress? This will be m upon z, where z is the section modulus. So m external, so whatever external force, external moment is acting, that divided by z, section modulus of the beam, this is the tensile stress that will come because of the external superimposed load. Now I have applied so this pre-stressing over it. Now because of pre-stressing, but I have applied eccentric pre-stress. Eccentric pre-stress I have given, this is the neutral plane, this is the eccentric pre-stress I have given. Now in order to understand its effect, I can do this. I can transform into, this is equivalent to what? This is equivalent to this into this, P into E. It was acting at a distance eccentricity of E. So this P will have an equal effect as this case. When pre-stressing force is acting at the neutral axis and the hogging moment of P into E magnitude is also acting at the neutral axis. This will have the same effect as the eccentric P force. Okay, so now we have to see from here. So when a compressive axial force will act on the beam, what will happen? Throughout its compression, throughout its cross section, compression will develop. Throughout its cross section, okay, compression will develop. And what is the magnitude of that compression? P by BD. Obviously, because where B and D are the area of the cross section of the beam, so P by BD is the total compressive stress that will develop throughout the cross section, at the top also, at the bottom also. Okay. Next thing, there is this hogging bending moment also. Now we have to take that into consideration as well. So this will create tension in the top portion and compression in the bottom portion, and the value of this maximum compression and tension will be equal to m upon z, again where m is equal to P into E. Here the bending moment is equal to the value of the moment, so that is P into E upon z, but here it is positive, this portion is positive, at top it will be negative. So this is because of pre-stressing, this is because of external loading. Okay, so because of external loading, it was because of external loading. Suppose this m is basically acting on over this. Because of this external loading, what we were getting earlier, we were getting this m upon m external upon z we were getting earlier, and this was negative, this positive. So combined, what we want ki compression might come in the upward direction, but tension here should be equal to 0. This is what we want. Total what do we want? So we have to find the value of EMX in such a way that the final the stress distribution looks like this. there should be no tension at the bottom. Okay, so now what I can do is I have written this, and now I have to add this also. So this becomes equal to P by BD plus PE upon Z. This must be equal to 0. I have to find the value from external such that summation of all these terms is equal to 0. Now first I have to write what is the value of section modulus Z. Now Z, as we know, that is equal to I upon Y max. I for a rectangular beam will be BD cube by 12, and Y max is the maximum distance of the extreme fiber from the neutral axis, so this will be equal to D by 2. Here D is not effective depth, D is total depth of the beam. Okay, so this is equal to BD square by 6. So B was 250, this is 600 square, this divided by 6, we get 250 into, okay, this is equal to 250 into, okay, this is 15 into 10 raised to power 6 mm cube. This is the section modulus. I have to use this value here only. And what is the value of P? We have found out the value of P is 157.25 kilonewton. This is the value of P. Okay, this is the value of P. So now I'll use this here. So M external I have to find. M external should be equal to divided by Z. Z was 15 into 6. This must be equal to what? P. P was 157.25 है ना, 157.25 divided by B divided by D plus P into E. P into E is, E was 100 divided by again Z, which is 15 into 6. Okay, from here I can find the value of M external. So let me write what is find this value, and this value is 157.25 divided by 250 divided by 600. This is 1.048 into 10 raised to power minus 3. This value is 157.25 divided by 15 divided by this. So this is again 0.148 into 10 raised to power minus 3. Now this value is to be multiplied by 15 into 10 raised to power 6. 15 into 10 raised to power 6. So this becomes 1.048 twice into 15 . This is equal to 13440 kilonewton millimeter, because we have put our force in kilonewton and we have put our dimension, linear dimension, in millimeter. So this is the maximum bending moment that can be applied. By applying this maximum bending moment, we'll have zero tension at that. We can convert into kilonewton meter, which is the most common unit, that it will be equal to 31.44 kilonewton meter. This is the maximum bending stress we can apply. Now we can check the option, that which option will suit this. So we have to move to the question. So question was, okay, so we have 31, 36, 38. So 31.4, which is equal to 31.5. So this option C is correct for this case. Okay, so that's it from my side. Thank you very much for listening to my video, and I hope you I wish you all the best for your future endeavors. Okay, thank you.